To begin, basically, what we're going to do is we're going to look at field effect transistors. So those are FETs. Field effect transistors, which are FET devices. Okay, and for field effect transistors, one we're going to look at is the junction field effect transistor. So that's a JFET, the junction field effect transistor. And what is special about a JFET? It basically is a unipolar device. What does that mean? Well, when it's unipolar, it means only electrons or only holes can flow through it, not both. So it's either has holes flowing or either has electrons flowing, not like a bipolar junction transistor, which has holes and electron flows. We can have, it's a voltage controlled device. That's with our field effect transistors. You apply voltage at the gate, so voltage controlled device. And then basically, that's basically your voltage between the gate and the source. You'll see that often, and you'll see ID, the curves of the voltage between the gate and the source, and you choose a VG, and then you'll backtrack it, and then that determines your ID. And so that's the drain current, and then it's a high input impedance. That's with a JFET. And so what you need to know is it operates in reverse bias. So that's why it has high, sorry, that's an R there for reverse bias. That's why it has high input impedance, because if you look specifically at the curve of a diode, right? Let me draw it real quick. And we look at our curve here. Something like this, right? But if you look at, this is like the voltage, you know, and then this is the current. And so we have our current and we have our voltage, but to get resistance, you do voltage divided by current, right? And if you look at the resistance in the reverse bias region, which is over here, you do the voltage, there's literally, you can see that the voltage is changing. So like this would be like -10 volts to get to this region where we have the breakdown. And then like right here is 0 volts where we start out. So it's like a change of 10. But if you look at the current, it barely changes along here. There's like almost no change in the current, because remember, you do resistance equals voltage over current. But here we can see from the slope of this line that for if you like do tangent line to get the slope, what we're going to see is this line, the resistance, if it's the voltage, the change in voltage is just 10, and there's barely any change in current. It's like 0.001. So it's almost infinite. So that's why we say it has a high input impedance. It's like almost infinite. But you're going to see when we do the input resistance, what it's going to actually equal for our input. I'll write it later, but it's R1 in parallel with R2. And then these are preferred for switching applications, just FETs in general. When I say that, MOSFETs we'll see a lot of times used, enhancement MOSFETs. And what does this look like? Okay, let's draw a diagram and just try understanding the internal mechanisms of a junction field effect transistor. And so when we have our field effect transistor, it's going to be like a box like this almost, I like to draw. And here within our box, we have two substrates. One here, one here. And then we have our channel, basically our main substrate in here, and then we dope it with these other material. A lot of times, for an N channel device versus a P channel device. So here, let me draw the N channel on the left. If it's an N channel, that means this must be the N part. These are the P parts here. Because the N is the channel. Because this is our channel length right here. Let me just This is our channel, so where it's going to flow through there. And so that is basically what we have for the flow of current. And here are other sides, but what we're going to notice is that our P channels, on the other hand, that's when you use P as the majority substrate and you dope it with the N on the outer side. So here we have our N doped, and here's the P. There you go. And so this is a P channel because the majority is P substrate. And so all the flow is going to be happening in here from one side to the other. And then we need to know with these devices, we have a gate. So here's our gate we can think of. And then we have a drain and a source. So here we can think of as our source. And here we can think of it as our drain, where it goes to. Here, same thing. We have a gate here. We have a source. And we have a drain. So drain is like where it goes to when it flows, right? Like it drains out of, so we can see the arrows pointing in that direction towards the drain. And then same thing here, if we have the current flow go from the source to the drain. And so now what we're going to notice is when we get a large electric field, so I'm gonna do this flow. When we have a large electric field, that means we have minimum current. But when we have a small electric field, that means we have maximum current flow. So let's see why. So when we have a large electric field, that means that basically what's going to build up is we're going to see this layer right here. It's going to affect the lightly doped, remember. And when we basically crank up, I want you to see the curves so you understand this. So let me draw the curve below. ID. And then here is our VGS. And then remember the characteristic curves. They basically look something like this. We have something like this. Something like that. And these are basically what our curves appear as. And what we're going to see, remember there's a max value of current that you can hit, which is IDSS, the max value of current for that specific curve. And the point where VGS, where the current is 0, this is the VGS off point, where the current is 0. So where the current is 0 and where your max amount of current for your curve is IDSS. It's the maximum amount of current you have, and that's going between the drain and source. Here, this is the voltage applied at the gate and source. So this is the maximum amount of voltage you would apply. And so it would shut off any current flow. And you would have almost no current flow because we have a minimized channel. And so what's going to happen is an electric field's going to build up. We'll see when we apply a VGS, remember this is reverse bias. That's how these work. But when we apply a VGS specifically between the gate and the source, what is going to happen is that for that specific reverse bias, we're going to see that an electric field is going to build up in once the it affects from the lightly doped side, and it's going to cause that channel width to be depleted. And so due to the depletion region increasing, because we're in reverse bias, remember this comes from a BJT. I'll just draw it on the side a little bit. Remember how we had the emitter, the base, the collector terminals. And then we had the forward bias junction here, and then we had the reverse bias junction. And we had like a little depletion layer within here. And so remember, it affected the lightly doped region the most. And so what we're going to see is that it's going to affect the lightly doped regions, and that's where the buildup of the depletion region will be. And when there's a buildup depletion region, it's going to make it harder and harder for current to flow through because the channel is made narrower. And so since the channel is being made narrower, that means that we're applying more reverse bias voltage. So basically, right here, I can write to the left of this, bigger VGS, you're going to have a larger electric field, so you're going to have minimum current. But a smaller VGS means that you have a smaller electric field, because remember, voltage is equal to the negative integral of E dx. And so when you have a smaller voltage, you have a smaller electric field, they're proportional to one another. And then if you have smaller electric field, then you have maximum current. Since there's only like a little bit, not much. And so there's still a lot of current able to flow through this device. And so you still have a large channel. And so that's what we're going to see. When you have IDSS maximized, that means you have a large channel. When you have VGS off, you're going to have a narrow channel. So that's an important part to take away. So IDSS is found with a wide channel because that's a maximum amount of current flow. And VGS off is found with a narrow channel because there's no current flow. Okay. And now we need to talk a little bit about what our circuit setup would look like for a JFET. How does a JFET look? And so a JFET, basically we have here, here, and this is going to be our gate on this side. And we oftentimes have the arrow pointing inwards. Usually we deal with, I believe this is for the P channel device. I need to double check on that. But D, and then we have S here. And so what we're going to see is basically for this, we're going to have forward bias for the voltage between the drain and source. And remember, our gate to source is reverse bias because that's where we operate in this VGS. You operate in the reverse bias region. We're in the negative volts, and we're not in the positive domain. We're in the negative. So that's why the voltage between the gate and source, it operates reverse bias, and that's how this junction field effect transistor works, where the voltage between the drain and source, this is going to be a positive voltage, where this is a negative. Okay, and so what you need to know specifically, let me write down these equations, is when VGS is equal to 0 volts, we're at IDSX, right? So that's the maximum amount of current. So ID equals IDSS, which is the max current that can go through the JFET. So through JFET. Since that's a max current for the drain FET, that must mean that this is well, if we apply no voltage, we get the maximum amount of current. So that must mean it's a normally on device. And we'll see when VGS equals VGS off, ID equals 0. So minimum current. And so that means you have to apply voltage to turn the device off. So there will be no current flow. So you must apply apply a voltage to turn off. Okay. Now that we talked about that, we're going to have drain curves for this specific device. So our drain curves, they look something like this, where we have ID and VDS. And so we have a list of curves, we have our IDSS point, where that's the maximum amount of current. But we have, I'll just in a different color, it builds up and then it flattens out. And then we see this with the other ones, builds up, flattens out, builds up, flattens out, builds up, flattens out. Okay, and so at these, this is when VGS is equal to 0. This is when VGS is equal to -1, this curve down here, -2, -3, and then usually the smallest ones, what we see on devices is like -4. And so let's label the regions. So this region right here is the ohmic or linear region. And so that means basically it's acting like a resistance, right? Because it's pretty constant. Resistors, if we look at their curve of the amount of current and amount of voltage, it basically is a line for a resistor. And so that's the same thing here. It's just like a line. So at the beginning, it acts like a resistor. And then what you're going to see is in this mode right here, this part right here, not including this part down here, this is a separate one. But this yellow part here is known for being our saturated region. This pink part down here is the pinch-off region. And if you were to encounter a breakdown, it would be when you go upwards, like so if the curve went up like this, like that. This would be your break-off region where it'd start going up dramatically. But what you need to know is basically right at this point right here, where we go from our ohmic region to our saturated region. This is the voltage, the pinch-off voltage, what we're going to see when VDS is greater than the pinch-off voltage, the current will saturate through the device. So that will get to that constant region almost. It's almost constant. So current will saturate through the device. And so even if VDS increases, which we see here, it's going to be about the same amount of current. And then what we're going to notice is for the curves, if I put them next to one another, so let me do it here. ID, and let's look at both of them, the input and the output curves. And so what we're going to notice, VGS is on this side, or VDS is on this side. And what we have seen for a normal one, I forgot what our VGS off is in the lab, but I'm just going to say it's 4 volts because normally it's 4 volts for some devices when I looked at charts for VGS off. So this is our VGS off at 4. And we can reach a maximum value for current, which is IDSS. So if this is our VGS off point and we know the maximum value of current IDSS, we can make our curve look something like that. And then we can draw our output characteristic curves. My first one, I know it's going to saturate at that point. And then my next one, because if you back trace it here, that's going to be the point where it intercepts with the current. So then if I look at -1 volt, if I back trace that over here, we're going to see that the current will saturate there. So if I go, looks like that. Then if I look at -2 volts, it intercepts the curve there. So it's going to go around right here. And then if I look at -3 volts, back trace it, it's about there. And there we go. So that basically tells us how you can draw the VGS curve. So this is VGS equals 0, -1, -2, -3. And so what we're going to see here is that these is when you have, remember, this is reverse bias for your VGS, where this, we're going to see for input, we don't operate in the forward bias, because if you operate in the forward bias, the input resistance is about 0, is approximately 0. It's like so small. And if you get such a small input resistance, why are you using a JFET in the first place? It has a high input resistance, which you want, is we use these with transducers. And then this curve right here is described by Shockley's equation. Sorry if I mispronounced this guy's name or if I spelled it wrong. There's too many people who we know for formulas, so I don't care anymore. Shockley's equation, but I know the correct format for his equation. That's all that matters. So ID is equal to IDSS, and then it's 1 minus VGS over VGS off. And then this is squared. It's a square law device. So you square it. And that's what we have here. You can see it is squared. So it's ID equals IDSS, and then 1 minus VGS over VGS off. And then you square it. That's why it's known as a square law device. And then we know the voltage gain. We have to determine that for this device. So we know the equation to find ID for this device, but now we need to determine the voltage gain. And so within our setup, most of the time for these types of devices, for voltage gain, it will be, let me draw it out for you to correspond with your voltage gain. So what you've seen with BJTs for JFETs as well. So let me draw the circuit diagram real quick so you understand where this voltage gain is coming from. So this one. Then then we have a bypass capacitor usually. And now that we've drawn this, this is usually the voltage source up here. When you deal with MOSFETs and JFETs, it's VDD. And then the current, this is known as the drain, gate, and source. So this is RD here. This is RS down here. We have a capacitor, a bypass capacitor. This is R1. This is R2. And then what we need to know about this device, like with our JFETs in particular, is, remember how we had voltage gain? Let me write over here for BJTs. We would usually follow this format. It'd be RC over 1 over GM plus RE. That was for BJTs we oftentimes use. And if we had a bypass capacitor, so with a bypass capacitor, oh, sorry, I forgot the name this time here. It became, RE became 0. And so this went towards 0 because the capacitor made the effective impedance 0. And then this would become AV equals negative GMRC. Well, here, our gain equation is given by negative RD all over 1 over GM plus R of S. So the exact same format, except the capacitor here in parallel of R of S is going to make this term go to 0. So we're going to get negative GMRD. And this would be when you have a bypass capacitor. If you don't have the bypass capacitor, you follow this gain equation because RS doesn't go towards 0. But because of this parallel combination of RS and C, its effective impedance is 0. And so that's why we get this gain equation. And then now that we studied that, what we're going to see is there's different types of biasing you can do on these devices. So let's talk about the biasing, how we can do it. And so the first type is self-biasing. So self-biasing. And for self-biasing, what we're going to see is, let me draw the curve here. Remember, this is your input when you do self-biasing. It's going to affect the input curves. It's basically you'll put the gate at 0 volts. And so what you're going to see here is, here's our normal curve, like I drew above, right, in pink. So let me match that up. Looks something like this. That's our normal curve. So the self-biasing approach takes it sets it at 0, your VGS, and it basically just your RVS, what you're going to see is this slope of the line is, remember, this is VGS, this is ID. And so ID over VGS, that's going to give you 1 over the resistance. So it's 1 over R of S, the slope of this line here. And so this slope of the line will be determined by your resistor R of S. And so this would be your maximum point here. And then your minimum point is going to come from your skinny channel. And so like my skinny channel is something like this. This would be your minimum point. And so you got your max, you got your minimum. And so that would be self-biasing. And so what it looks like on your circuit is you put the gate at 0. Then you have your 2 resistors, RD, and your resistor RVS. And remember, RVS is determined due to the slope of this line. When you choose your RVS, that's going to determine the slope. And then you're going to back trace from where it intercepts the fat channel and the skinny channel. Wide or narrow, same thing. And then you're going to back trace it so when it intersects with ID, and you'll get your minimum and maximum point. And you can tell that there's a bit of difference between the min and max point here. So there is a little variation in ID here. And so we want to minimize that variation. And so let's look at another technique, which is fixed biasing. So fixed biasing what's going to happen is we're going to fix basically the voltage between the gate and source. And so this is what you're going to see. So it's going to fix voltage. I just like connecting names to things. So that's where the fix comes in. So fixed voltage between gate and source. And so here we have our curves, which look like this and this. So we have our VGS, and we have our ID, and we have our min and max. So we have, our narrow channel and our wide channel. And then we have a fixed VGS, a fixed voltage between the gate and source. So it's going to look like that. Fixed voltage. So this would be our VGS fixed. And so what we're going to notice is that this is going to be our maximum current, where we backtrace the graph, and this will be our minimum current. And you can tell there is a wide difference in ID here. There's a pretty wide difference, which we don't want. And you can see the circuit diagram, if that helps you understand it better. Oops. This is going to happen. This will have a positive. Okay, so this is the voltage between the gate and source. This is our R of S. This is our RD. And so what we're going to notice is that there's a wide variation in the min and max point. So we don't like that because our current can change too largely. And so this isn't a good biasing technique to get the operating point we want. That's why we bias. Sorry, I should have said that here. It's to get our operating point. Okay. And then the third one is combination biasing. So combination biasing, this technique we like. So yay, smiley face. We want to use this one. So there's little separation between the minimum and maximum. And so that's why we like it. So let's draw our curve again. We'll have our ID, and then here we have our VGS. And so we have our narrow, and we have our wide channel. And then here, what we do is we pick a value of voltage at the gate, in particular that we're going to apply. And so what's going to happen here is we're going to see that the particular voltage we apply at the gate out here, so VG, if we backtrace that, what we have to do is the important thing, the voltage at the gate for the narrow channel, right? That's the minimum amount of current you'll get going through. You don't want to exceed that. So I don't want to draw my line. Let me just show you real quick. I don't want to draw above. This is what you don't want to do. So don't follow what I'm doing right now. But this is what you don't want to do because it exceeds that minimum current going through channel. So that means it's going to take this actually when it's in forward bias for VGS, because right now we're operating in the reverse bias region over here. But that would cause us to go in the forward bias region. So that would get rid of all our input resistance, which we don't want. We want high input resistance. And so we want it to intercept with the minimum amount of current. And then we don't want it to go in the force-fed region. So that's why we intercept the minimum amount of current. So it stays in the reverse bias region. And then what we're going to notice here is when you backtrace the graph in particular, this is your max point. Then right here is your min point. You can tell there is almost such little difference in the drain current that honestly, this is the best technique because you have such little variation in the current that is going to be running through your device. And so that's why we like the combination biasing, because it helps to make sure that we have a stable operating point, that it's not going to fluctuate. So we have our R1, and we have our R2. R1, R2. This is just the circuit diagram visual to help you. This is our RD. Here's our VDD. Here is our JFET. And here's our R of S. Okay, and so the voltage at the gate, that would be like our external, how we would apply like a voltage here. There you go. It'd be something like that. Voltage at the gate is applied specifically, or what happens is we can also do it this way. So ignore this, and you can use the source, sorry. And then from your source, what you do is you apply a certain amount of voltage to be dedicated to the voltage at the gate. So it might be VG here, and you make a voltage division equation. So VG is equal to VDD multiplied by R2 all over R1 plus R2. There you go. And so that is another technique. And so the two next ones I just want to run through real quick is just how do we determine which equations we should use for input, output, resistance, and gain. So let's look, here's the two common types of designs that, well, I guess there's three, just you're fully degenerated, you're partially degenerated, and you're not degenerated. And so let's just run through the different configurations. So configurations of JFETs. So the configurations of a JFET, the first one would be, let's do not degenerated. So if we do not degenerated, I'm gonna have, okay, degenerated means you decrease the gain. And so if we want to maximize our gain, we're going to use a bypass capacitor. So here, and VDD, and then we have all the process. And so, and then what we're going to notice in particular with our JFET device is we're going to have, because it's not degenerated, that's the reason why we have this bypass capacitor, because it's going to make a large gain. And so here we have our R1, here's our R2, here's our RD, and here's our RS. And so what we're going to notice is the input resistance, Rin, is going to be R1 in parallel with R2. And then our R out is going to equal RD, about approximately RD, because it's RD in parallel with RO to be exact, but our output resistance is basically almost equivalent to RD. So that's what you need to know. And then our AV, since we have maximized gain, it's going to be negative GM RD, because we can ignore R of S because it's about 0, the parallel combination. And then our partially degenerated design.
Yo, Brian, shouldn't RO be like 90% of RO, like big RO? Because I remember it was like 90%.
Of, oh, like about 90% of RD.
So yeah, something like that.
Yeah, it's like,
90%.
that's why I said it's about RD. It's like pretty close. Like it's, okay, if RD is like 1.2K or something, like R out could be like 1.1K, but it's like close enough where it's like, you know, it's going to fluctuate a little the current as well, so it won't make a huge difference. So we just made the estimate. It's about RD. And then it's fine though, Tom, if you do 90% of it, just as long as it's close to RD, because we make a lot of estimates already, so you're good. Okay, so the partially degenerated is RD. Then here we have our bypass capacitor, but it's only hooked up to one of them. And so what we're going to see, RS2, this is RS1, our R input is still going to equal R1 in parallel of R2. Our R output is still going to be roughly RD. And then our AV is going to be equal to, and then it's going to be RD all over 1 over GM plus RS1. And then that is what you'll get for your gain equation there. And because we had to now take into account our vest because one of them was not bypassed, so it did not go to 0. And our third type of configuration, we have not degenerated. We did partially not degenerated, so now we need to do a fully degenerated design. So that means you'll have very little gain. So fully degenerated. So it's going to look like this. VDD here, RD, JFET here. And another one, but we don't have a bypass capacitor anymore. So RFS, RP, R1, R2. So your input resistance Rin is going to be R1 in parallel to R2. Your output resistance is going to be about RD still, but your gain is going to equal. And then remember our equation where we had RD over 1 over GM plus R of S? Well, what's going to happen here is I always forgot this negative in here, right down there. So make sure you add in that negative. But here, our RS now has to be taken into account since we don't have a bypass capacitor. And so use this equation. You can approximate it, but sometimes it depends on what your transconductance is, your GM. But it's going to be approximately RD over RS. That's your approximate value. And now that sums up basically what you should have expected with your JFET device. So let's turn over to some problems. So let's do an example one. So let's just start from the beginning. So one example I say we should probably start out with is this one on the very left. So let's just get used to JFETs, how they work. So find ID and VDS in the circuits below. So for this first example here, let me move this over. You can see it. Okay, we have in -8 volts. We have one resistor here, and a resistor here. We have 1K, and we have 7K. And then here, we got our JFET device, and it's hooked to ground. We have no RVS, but we have a drain resistor. And this is hooked to 10 volts. This is 300 ohms. Okay. So what do we need to do? Find ID and VDS in the 3 circuits. Okay, so right here, it didn't tell us which type of JFET, but he gave us some curves here. And so let's look at the curves here for this device because we need to look at the input curves in particular, and we need to see what should be happening here. So when I'm trying to think of this device, we have to determine, it said in the problem, ID. So that's one of our unknowns we need to find, and VDS. Okay, to find ID, what should I do? I remember the square law equation. I don't know if that comes to mind, but that's one thing that I would think of. ID is equal to IDSS, and then it's, after we see that, it's 1 minus VGS all over VGS off, and then you square it. And so here, when I'm looking at this curve down here, you can see right here, when I'm analyzing it, do you agree with me? This is the maximum point of current right here, IDSS. So that's what my IDSS is here. And then my VGS off, it looks like, is -4 volts. So that's my VGS off here, -4 volts. And so I know those two, but what's my voltage between the gate and the source? And so we need to determine that. So right now I can plug in 32, and then this is milliamps, 1 minus, and then my VGS off is 4 or -4 volts. But let's see, what is our VGS? Our VGS, well, let's find out how much voltage is actually at the gate. So the voltage at the gate, VG is equal to, and then this will be a voltage division problem, right? -8 volts times 1K all over 1K plus 7K. Okay, when I do this, what I get in my circuit is I get -8 times, and then 1 divided by 8, which is going to be -1 volt. Okay, so I got my VG, but now we need to find VGS. So voltage between the gate and source is going to equal the voltage at the gate minus the voltage at the source. Right here we have -1 volt, and the voltage at the source is set at 0 volts because this is our source, remember? This is our drain up here, but the source is connected to 0 volts. So the voltage between the gate and source we're going to see is equal to -1 volt. So this would be a -1 all over. And so what we're going to tell though, when we are working with these devices, one thing that I'm going to say is that this number has to be less than 1, right? And so let me clear my annotations real quick. This number has to be less than 1 inside of here. And the reason why I'm saying that is because if it was greater than 1, then that would be multiplied by IDSS and it exceed the maximum amount of current the device can handle. So within this, when I do 1 minus, this turns into a positive number because negative over negative, so it would be positive 1/4. So we actually 3/4 squared times 32 milliamps. And then this is going to be 3 divided by 4, square it, times 32 milliamps. I got 18 milliamps for my ID. And so I found my ID, what it is equal to, and my voltage between the drain and source. So the voltage between the drain and source, that's going to equal the voltage at the drain minus the voltage at the source. So here, my voltage at the drain, well, we know ID right now, which is the current going through here. So it can equal this one drop here, that'd be the voltage at the drain, then we minus that from the voltage at the source, which is set at 0. So this would equal 300 ohms times 18 milliamps minus 0, which is going to be 300 times 18 milliamps. I got 5.4 volts. And that is how I determined ID and VDS. And so that's what I got there. I'll give you guys a second. Now we're going to go to C, because now we determined VDS and ID. So the next example we're going to do is going to be 25K and 5K. We have a 25K and 5K ohm resistor. This is hooked to ground. This right here is for 10K. Here's our 6K. And here's our 12 volt. And they'll be asking you oftentimes, what's ID and what is VDS? So here, we don't have two sources like the one above. Here we had two sources, and the reason we don't use that in practical circuits is because that's two different supplies and that it's more money. So we just use one supply. But what we can do here is we can still determine how much voltage is at the gate. And that's going to help us because we're going to use our combination biasing technique. So the voltage at the gate, VG, is equal to 12 volts from the source multiplied by 5K over 5K plus 25K. And so that is 5 over 30, which is going to be 5 over 30 is 1/6 of the amount. So 1/6 times 12, that would be 2. So voltage at the gate equals 2 volts. So we have 2 volts here. Now let's look at the curve specifically. If we have 2 volts, I'm going to look at this curve and try guesstimating where that would be. So if this is for 1 volt here, I would say that's about here. This is where 1 volt is. And if I had to equally space, I would say this is about where 2 volts is. If I were graphing it, does that look like the same distance here? Maybe it's just a little wider. Maybe I should have put it here. Let me erase this one. Okay, and now I know my VG, and I know specifically my channel. So what we're going to do is we're going to connect our VG. We have to draw a line. And remember, so I'm just going to draw an arbitrary line here. And then remember with our line, it has to be 1 over RS, the slope of it. And we are given our value for RS right here, 6K. And so 1 over 6K. So let me just draw this curve here. It's not going to look as good, but I'm going to just replicate that curve. So we have something. And then -4 to 32. And 2 milliamps, and then -4 volts. And so remember the slope of the line here, because we know we need to apply 2 volts for VG, and then we're drawing it. The slope of our line is 1 over RS, which is going to equal 1 over our RS is 6K, which is 1 divided by 6K. I have 166.67 micro. That's what I got specifically for what the slope of our line, what we're going to see. And so right here, if I have to look at where would that intercept my line, because going here, we're going to have to make that slope so that it is going to correspond with that line we have to draw. And what I'm thinking is, well, this would be 2. And then let's see, it's about like 6 volts here total. But if I did specifically 6 volts times the slope that it's following for each unit, so times 6, the difference between, I got 1 milliamp at this point here. For my -4, it's about 1 milliamp. So if I'm looking on my curve right here, 1 milliamp would be about here. 1 milliamp. So if I'm going to look at that point specifically, it should intercept about, so at -4, it should be about here. At -1, sorry, for -4 volts, because there's 6 volts difference between here, and we determined the slope. So 6 volts times that slope, because that'd be how much we're moving the x direction. So how much would that y coordinate be? We determined it was 1 milliamp. And so now that we got that, we can draw our line. So let me erase this other line. I was just showing you how the slope, you determine that line. So here it's at we're at 2 volts for the voltage at the gate. It intercepts this point right here. And so now that we got that point, now we can back trace our graph to find out what current that will be. And it looks like it intercepts right about here, which is, let me make this straight. If I had to give the best idea, I would say about like 1.3 or something, 1.2 milliamps maybe. And so I would say that's about 1.2 milliamps. And so since we know that's 1.2 milliamps, we were able to back trace it to that point And when we looked at it, let me just know. We determined it was 1.2 milliamps for ID, something around there. So that's ID is equal to 1.2 milliamps. Then we're going to have to determine the voltage between the drain and source. And so the voltage between the drain and source, remember, voltage between the drain and source equals voltage at the drain minus voltage at the source. Determine the voltage at the drain, that's 10K times 1.2 milliamps minus, and then voltage at the source is going to be 6K times 1.2 milliamps. This is going to equal, when I do that in my calculator, I get 10. I got 4.8 volts. So I got 4.8 volts for my VDS. And I got 1.2 milliamps for my ID. And that's how I was able to determine it. Okay, now let's look at a design problem. So it says design a common source amplifier using a 2N4340 and a 12 volt supply. So here, what we do, design a common source amplifier. That's just our basic diagram. So go back to the basics. So we're going to have 12 volt supply. We're going to have a 2N4340 in our JFET device. And then we're going to have our ID, it says, is going to be within that range. And so what we're going to see here is we have to deliver a certain amount of voltage at the gate. But if we put more voltage at the gate, that's going to be less change in ID, which, because if we apply more voltage at the gate, that means there's less difference between the min and maximum current. And so what we're looking at is basically, we know our ID has to be between 1 milliamp. So our range of ID here says within 20%. So 1.2 milliamps is the max and 0.8 milliamps is the minimum. That's what we have as our range. Find AB for a narrow channel device and for a wide channel device. So we need to determine the gain for this device. And let's look at the data sheet for this one. So for the 2N4340 data sheet, these are some important characteristics which he might give us from the sheets. Access 59. Okay, for the 4340 right here, it tells us the IDSS is between 1.2 to 3.6. And then it says the VGS off is between 1 to 3. So let me just draw my little characteristic curve here for a fat and narrow channel device. So here we go. Okay, so my VGS, it says is between 1 to 3. So here it would be like 1, 2, 3. So this is our VGS. So this would be -3, -2, -1, 0. And then our IDSS is going to be 1.2 to 3.6. So if I did 1.2 here, and then this one, 2.4, 3.6. This is our ID, that's our VGS. And then I have to determine the curves. So the narrow channel device would be the minimum to the minimum, and our wide channel device would be from the max to the max, something like that. And so those are my curves. And now I need to determine, I got my current, I got my curves. We have to find, in order that this device basically is going to have a maximum drain current of 1.2 milliamps. So that means on the fat channel, it needs to intercept this point here. And so we know that has to intercept that specific point for our VG. And when I'm looking at it, we don't want it to fall below 0.8. So our 0.8, if this is 0.4, 0.8 would be about here. Let's see. So this would be 0.8. It's about 2/3 of the way up on that unit. And then I have to draw a curve. It should be here. That's about what I see. So let's roughly estimate 1, 2, 3, 5. I'm going to say that's about 5 volts for a VG. So this is going to be what our VG is. And then now that I determined the voltage at the gate that I must supply here, so this must be about 5 volts from these curves, what I guesstimated. This must mean that in order to get 5 volts there, this must be 5 mega ohms, whereas this must be 7 mega ohms. Because if you do voltage division for voltage at the gate, it's going to equal 12 times, and then this is going to be 5 megs over 5 megs plus 7 megs. And so, oh, sorry, if we have our 12 times 5 mega ohms, 5 mega ohms plus 7 mega ohms, I got 5 volts for VG. So that's what we determined here. And so now that we found VG, what it has to be, we need to do, what can we say? So now we found out what our VG was, we need to still determine these resistors here. And so, what did it say in the problem? It said we need to find the gain for a narrow channel and for a wide channel device. So we still need to determine these resistor values here. And so our typical current that we're going to have flowing through here is 1 milliamp, right? Because there would be our typical curve in between. And that's going to intercept right about 1 milliamp. So ID is typically 1 milliamp, right? Okay. So if we know ID is typically 1 milliamp, then what else do we need to determine? So we know our VGS, we know that would be okay, this is where it's going to come down specifically to how much gain do you want on your device to determine how much voltage your device can handle. And so you're going to use an equation basically to determine your voltage on VRD, but when I'm looking at this specifically, we have to choose a value because remember, gain is always going to be how much is on this resistor over this resistor here. And that's going to determine how much gain we're going to get for a device. And that's a pretty important aspect. And so, okay, so our VRVS, what we're going to see is that basically to calculate your VRVS, you're going to have to determine right here, there's about 5 volts. Then you take into account the worst case scenario where this is 1.8 volts difference between the two. So it's about 6.8 volts. How much has to be allocated for your R of S and divide by the current. Oh, okay. This makes sense now because what you need to look at, remember, this is the slope of the line, 1 over R of S. Now it's making sense. And so right here we have, in order to determine R of S though, it's the voltage over the current. So we need to find the change in the voltage over the change in the current, which we just did right here. So we did 6.8 volts divided by 1.2 milliamps. That's how we got VR of S. And now that we do that, 6.8 divided by 1.2 milliamps, I got 5.6 volts, 5.67 volts Okay, now that we got that for VR of S, our resistor value is going to be VR of S, sorry, because that's volts divided by current. This is actually R of S. Oopsies. And so this is 5.67 kiloohms. Let me fix that. Kiloohms. Now that we got R of S, we need to determine what RD should be. So we got 5.67 kiloohms. And then here we need to determine RD still. And so to determine RD, what we're going to do is the voltage on RD is going to equal the supply minus, so VDD minus, and then here it's going to be, what we're going to have in here is the voltage on R of S. That makes sense because here minus this voltage drop, and then we're going to minus the voltage offset. So to take into account any offset voltage. And then for our last one, we can see from his equation. So within this equation, we also need to take into account minus VDS min. And so our VDS min would be like the minimum point, like you have to get into that saturation mode. So if you remember those saturation curves, that's what it would be. So I'm gonna minus a 0.5 approximately for like what that could be in order to get to that point. And so I have 12 minus 6.8 minus 2 minus 0.5. And I would get like a voltage, my VRD is going to equal 2.7 volts. And 2.7 divided by 1 milliamp typically for my RD is going to be 2.7 divided by 1 milliamp, which is 2.7 kiloohms. So we had 2.7 kiloohms, which is not going to provide much gain in our device here. So let me flip it over here. It's not going to provide much gain because remember the gain is going to be approximately here. If we design our common source amplifier, remember for the gain, it's equal to negative RD all over 1 over GM plus R of S. And here, what we have for our RD, the value of RD is less than R of S. However, if we use a bypass capacitor here, this value is now going to become 0, remember for a gain. So this becomes 0, then it's just going to equal negative GM/RD. And so then we'd have to determine GM, which if you remember transconductance, GM is equal to the incremental change in the output voltage, which is ID, all over the input voltage. So what you're going to have here is you would need to draw a tangent line to determine your G of M for these devices. And so your G of M here, if we're drawing a tangent line to the point where it intercepts, it's going to be here. And then a tangent line to the fat channel, it would be about here, where those two intercept. And so then our G of M for the narrow and the G of M for the wide. About when I'm looking at this wide channel, I think I might have drawn that. It should have been more like this. It intercepts coming in from this side. Let me see. I think that's better, or at least the tangent line. So use this one here. And then if you have to calculate our G of M for the narrow channel, that's going to be the change in current, which is right here. It looks like it intercepts about 1. So let me do the G of M for the narrow. It's going to equal 1 milliamp all over. Then the change in voltage here. This is approximately 0.6 volts, I would say. So 1 milli divided by 6. I got 166 micro. And so, oops, divided by 0.6, sorry. I got 1.66 milli. Okay, now that we know that, let's do our AV for the narrow. It's going to equal 1.66 milli times, and then RD is going to be 2.7K equals times 2.7K. I got 4.5. Then my AV for the wide channel, my G of M for the wide channel, it's going to equal, okay, this is about, if I had to guess, this is 2.4, 3.6 in between. That is going to be 3 milliamps. So this would be about, 3 milliamps all over. And then here it's going to be approximately, at this point, it is about 2.7 volts, which equals, and then here, oh, sorry, I forgot the negative in my gain equation, negative 4.5. This is 3 milliamps divided by 2.7. I got 1.11 milli. Up here for the, you'll notice that my G of M was larger for my narrow channel than it was for my wide channel. And then our AV for the wide is going to equal negative 1.11 milli times, and then this is going to be, our RV is 2.7K ohm, which is going to be 3. And then negative 3, sorry, forgot the sign in front. So we're going to notice that the gain is larger for a narrow channel than a wide channel. And so that you should take up on that fact. And now that we have discussed that, let's go on to MOSFETs. And so let's cover a little bit about what those can be. And so MOSFETs are different types of field effect transistors, and you're going to see why we like to use them. And so for MOSFETs devices, we're going to look at particularly the differences between the JFET and MOSFET, and then we'll dive into them. So JFET and MOSFET. These are both field effect transistors. So differences and similarities. And so the main difference, one of them, is that the gate is isolated for a MOSFET. So the gate is isolated from the channel. And the MOSFETs are more widely used in the industry. The last part is they operate with positive VGS, not a negative like we're used to. And they still have the same terminal names. They both have, drain, gate, source. They both have N and P channel devices. And they have a large input impedance. And they're both voltage controlled. And they're both unipolar. Now only one charge carrier flows through the channel. So what we're going to notice is basically we'll have our N channel and our P channel MOSFET device, and then we're going to have a depletion mode MOSFET and an enhancement mode MOSFET. And so the depletion mode MOSFETs, what those look like, just so depletion mode MOSFET. We have the N channel depletion mode MOSFET, so the N channel one, and then we have the P channel. So it would look like this. So within our MOSFET, for depletion mode, they're all interconnected. And then the arrow points inwards. And here we go. Where our P channel, we have okay. And it's still, you'll notice, you still have your gate, source, and drain. Same thing with this device right here. Still have your gate, source, and drain. Okay, now we need to have our enhancement mode MOSFETs. So this is where we have gaps. And so in the circuit symbol for the enhancement mode MOSFET, we still have the N channel and we have the P channel. And here for the N channel, it still points inwards, but the difference is there's gaps now. This one here. Where the P channel, it's going to be still gaps in between, but this one's going to be connected to this one down here, and this one will be up. Okay, so the depletion mode MOSFET, that one. How is that one? We'll look at that one first, and we'll look at the enhancement mode, so we're just familiar with both. And so this is most similar to the JFET. The reason why is an electric, when you apply VGS, it creates an electric field at the gate, which controls the current that flows through the field effect transistor. And so you're going to see, if we do our diagrams in particular, what's going to happen is for this one, we still have like our N and like your substrate, the main one. Then you'll have your other one, which is P here. And so here's your gate, your drain, and your source. Gate, drain, and source. And what you need to notice is that when you apply a VGS, what's going to happen is it's going to generate an electric field that controls the current running through. So the current right now is ID here. And there's going to be an electric field that is created when you apply specifically your voltage. It's going to cause this to expand. So it's going to limit then your channel. So that's what you're going to notice. And it's going to come in between and start making that channel smaller and smaller. Where you're going to see when we work with enhancement mode MOSFETs, on the other hand, what's going to happen is an enhancement MOSFET looks like this when we do my drain, my gate, and my source. And here, what we're going to see is we have our N, we have our P, and we have our N layer. And basically what happens is it's a normally off device. You can see here, you have all your different, you have your N, you have your P, and you have your N. But the big thing is you apply voltage so that ID can start flowing through. And so when you apply the voltage, it's actually going to go in this direction here, so you can start opening a channel for current to flow through. And so here you apply a voltage basically to open up the channel, and so it can flow through. And it's a positive voltage, remember. And so the nice thing is it's a normally off device. That's why we like enhancement modes, is they are normally off devices, and we apply a voltage at basically our VGS, a positive VGS is going to generate an electric field, and that electric field will cause the channel to open up so current can start flowing through. It's going to push this over this way. Whereas with our depletion mode, we have to apply voltage in order to close the channel to turn the device off. So this is normally on still. It's the closest to a JFET because they're both normally on devices. That's why we like enhancement mode, is because it is in normally off device here. And so that's why I just wrote over here, normally on and normally off. So that's the big thing about enhancement modes. You'll only see those used. And so what we're going to notice is that when you draw specifically the curve of ID versus VGS, so this is VGS, this is ID, and you're going to see that we're used to this characteristic curve here, you know, like something that looks like this. And this is when we have a negative VGS. We're in the negative region here. So this is our depletion mode. Where this is going to be our enhancement mode. So it's when we apply a positive VGS. So this is going to be our enhancement mode device. So enhance, something like that. It's going to be what we're used to seeing. It's the ability to control higher currents. And so what we're going to see within our depletion mode versus enhancement mode, you basically, this is normally off device, but you apply voltage in order to get a current running through. Here, it's going to be, you have to apply voltage to turn off this channel. And so here, you apply voltage to turn on the channel. That's the big thing to think of. And so now that we have dealt with that, let's look at some examples of MOSFETs and how we can use these devices particularly. And so another good comparison we should look at before we dive into some examples is going back to this diagram here of JFETs versus MOSFETs. Is that, remember for JFET, it's a square law device. ID equals IDSS, and then it's 1 minus VGS all over VP, or VGS off, I like that one more, than square. Where our MOSFET is ID equals K multiplied by VGS minus V Thevenin squared. And so, what we're going to notice here is they both have a square term in them. And there's this constant K though for the MOSFET, which we're gonna have to be working with now. And then when we're looking at specifically our gain ratio, remember for our JFETs, most of the time, it depends on which operation you have, but it's negative RD all over 1 over GM plus R of S. And then for your specific configurations, R of S goes to 0 sometimes. So sometimes it can be approximated by negative RD, negative GMRD, sorry, when you have a bypass capacitor. So let me put that down here, bypass capacitor. Okay, and so when you have a bypass capacitor, it's negative GMRD. And then our G of M here, what we're going to notice is, remember, transconductance is equal to, and then that is DID over, and then it's dVGS, because it's the output current over the input voltage. And then what we're going to see for this equation then, we take the derivative of the current with respect to VGS. What should you get as a result? And so we notice that it's within this exponential term here. So if we took that exponent out, right? So this would be, I'm going to write it down here since it's a little larger. It would be 2IDSS. And then what we would have here is 2IDSS. Then we get VG as minus VP. Graphically. Yes. One minus. Yeah, that term goes to 0 since this would just be a, if we distribute, what we notice is this one would just go, it's a constant, right? There's no VGS term, so that would go to 0. But this is the term that's going to change in our specific form. We get 1 minus VGS over VGS off. Then we do the derivative of the inside term, which would be, that would be derivative inside, this would be 1 over VGS off, because this is just the unit, so negative 1 over VGS off. And then what we're going to see is this is going to be 2 IDSS, and then it's going to be minus, and then that'd be 1 over VGS off. This would be over VGS off, and minus here, then be 1 minus VGS over VGS off. I think the equation in class they might have gave us was a little wrong. I need to double check that. Let's then, the GM though for this device, if we look for it with the change with respect to VGS, it's going to be K over 2, and then it's going to be VGS minus V Thevenin. The ID, changing ID over changing VGS. And so, give me a second real quick. Okay, so this equation, instead of just knowing this long one, what you should be familiar with is the GM is equal to 2 IDSS all over VP squared, and then it's VGS minus VP. And now that we determine that, and then we know this is K over 2 VGS minus VFab, let's look at specifically this sheet here, which tells us the major differences between BJTs and field effect transistors. Since now we covered the differences between MOSFETs and JFETs, let's just have a little bit of a deeper dive. And so what we're going to see is with our BJTs, you're going to notice we had the diffusion, which was an exponential process, and the output was given by specifically the saturation current, and an E to the VBE was our base to emitter voltage, which was, you know, what you had to supply, and then over VT, which was our thermal voltage. And the big thing here to take about is, remember, thermal voltage changes with temperature. So it's 0.26 millivolts at room temp. And so, 0.026 volts at room temp. And so that's at 25 degrees Celsius. However, at 19 degrees Celsius, this is going to go to 0.019, and at high temperatures such as 125 degrees Celsius, it is 0.035 volts. And so now that we talk about that, you can see from the curve, remember BJT, if you recall when you have your device, this was a diode drop between the base and the emitter. So it was about 0.7 volts in order to get current flowing through. So that's why here we have our 0.7 marks. In order to get current flowing through, it took about 0.7 volts. Our GM was the output current over, and then the voltage applied at the input. And so we noticed that VBE was for certain designs equivalent to VT. But when we took the derivative of IC with respect to VT, what we notice is it become 1 over VT in front. And so we got IBES over VT and then times E to the VBE over VT. And then here for the JFETs and MOSFETs, we need to notice that specifically the input is going to modulate how wide or narrow that channel is. And here we had an exponential process. Remember, we had the E to the output current was defined by an exponent relationship. Where here, we have the output current, but it's defined by this square right here. And so that square is causing us to have basically a little bit of a different output characteristic where it's more of a quadratic, where this is more exponential. And so that quadratic, we're going to notice specifically between the JFETs and the MOSFETs, these two equations, we have a constant for our MOSFETs, this K term, but this was, remember, IDSS was the maximum current, the pinch-off voltage to get into the saturation region. This is the voltage between the gate and source, and this was our pinch-off voltage. And then here's our ID equation for the MOSFET, which was K multiplied by VGS minus VFET squared. And so for JFETs, what we notice is they have to work in the negative region. So that's why it's 0. And then here we have our VGS off, which is synonymous with VP. And then we had our ID curve here with IDSS as the maximum amount of current. On the other hand, MOSFETs are positively controlled devices for their VGS, their enhancement mode. So they're controlled by positive voltages. And so that's why right here, you can see them on the right-hand side. And so that is for an enhancement mode MOSFET. And then they have these certain equations related with their transconductance. And so remember, transconductance is the derivative of ID with respect to VGS. It's given here. And so what we're going to see is we need to notice the difference between G of M and ID, what's happening. So G of M, loop right here, this is a big relationship which is going to determine your gain. And so ID has a square in it, where GM is linear. There's no square term on the outside here, no square term on the outside here. And so G of M is linear. ID is a square function. And so our gain is given by negative GM times RD, and our GM is linear, but our ID down here, remember, RD is just VRD over ID. Our ID is a squared, so this denominator is going to change faster than this numerator. And so because of that, what you're going to notice is that when your gain, if we see here, looking down here, GM divided by ID, if we compare it for the JFET and MOSFET, we have these two different equations here, but our gain is going to be determined by specifically the one that's going to change faster. And so if we have our ID changing faster, our gain is going to be more controlled by the effects of the ID than the GM. So you're going to notice that when we work through examples. And so the gain is going to be what we saw, GM over ID. When you set it equal in these equations, specifically, let me look for it. When we set them equal to, we got the output transconductance over the drain current. We got this for the JFET, this for the MOSFET. And so what you're going to see is the gain is going to increase as the voltage between the gate and source approaches the VGS off or V peak. And then what we're going to notice also is that between these devices, the major thing to pick up on is field effect transistors have infinite input impedance, and the bipolar junction transistors, their input impedance is limited, where the R output is equivalent to RC, but here it's equivalent to RD. And so that is the main things we need to know about. And then this right here is just a large equation, and I hate how it has these specific terms here, the coupling coefficients. I think it's better to write that the voltage on the load resistor is going to equal what you have specifically for your R in all over your R in plus, and then your generator, your function generator resistance, which I say RG for what's attached to your source resistance, times the gain of the device. So that would be then your output voltage right here. This determines your output voltage. So let me circle this. This is V out. And then how much of that output voltage actually gets to the load. And so then that's going to be your R load all over R load plus R output resistance. And that will determine how much voltage is on your load. And so that equation can be used to find your load voltage. And now that we talked about that, we have gone through the MOSFET comparison with our JFETs in particular. And so let's do a few examples to practice with the MOSFETs, and then we're going to run through the operational amplifiers. Okay, we're going to do these first few example ones of how to approach a MOSFET. You can see off the bat, this is a MOSFET. How would you know? Is because loop right here, it's an enhancement mode, and also at the device number. And 2N7000 is an enhancement mode MOSFET. You can also tell between the gaps between them. And then remember, this is an N channel, it's pointing inwards. And then same thing here, same thing here. So we're dealing with MOSFETs. So let's do an example of how to solve a MOSFET device. And so it says we need to find ID, VDS, R in, R out, and AB. So here we have this device. So let me look. This is 7 megs. Here we got 5 megs. And then we have this hooked to ground. We have 12 volts. Then we have 1.2K. Then we have, oops, these should have gaps in between. Let me fix that. Then this would be the voltage at the gate specifically, and then we have our N channel. Then here's our resistor on the source terminal, 500 ohms, and we got our capacitor. Okay. And so we need to find ID. So ID, VDS, RN, R out, and AB. Big thing is right here, we can determine already how much voltage is at the gate. It's a voltage division problem. The voltage at the gate is going to equal 12 multiplied by 5 megs over 5 megs plus 7 megs. And so that's what we're going to see. And so it'd be 5 volts. So we know V gate is equal to 5 volts. And then we have to determine, so find ID. So we know the voltage at the gate. And so that's a good thing. We know how much voltage we're applying there. And then looking at these characteristic curves for the 2N7000 V-shade device, our RVS here is 500 ohms. And so if our RVS, we need to find the slope of the line, which is 1 over RVS. Remember, that's always your slope here. It's given by 1 over RVS. And so 1 over RVS is going to equal 1 over 500. And when I do that, I get 1 divided by 500, which is 2 milli. So I got 2 milli, and our, so that'd be 0.002. It's going to travel, and we're going to see that the voltage specifically at the gate, what we had was 5 volts. So we're going to start here. And then we're going to travel 2 milli for each one. So if I do that 2 milli times 5, I should get 10 milliamps because 2 milli per unit. So 5 units, that gives me 10 milliamps. So now let me create a line in between my VG and my 10. Okay, now that I created that line, on the typical curve, my ID value intercepts at specifically, let's look here, you would say about here. For the typical curve, it's about like 5 milliamps. So ID is typically 5 milliamps. And then VDS, well, VDS is going to equal the voltage at the drain minus the voltage at the source. And so if we're looking at this in particular, the voltage at the drain is going to be 1.2 K times 5 milliamps minus 500 times 5 milliamps. VDS. And so right now we're not dealing with AC. We're just looking, this is a DC operating point. So that's why I took into account the 500 ohm resistor. 1.2 K times 5 milliamps minus 500 times 5 milliamps. I got 3.5 volts. For my VDS, now that I got 3.5 volts, I need to determine my Rin. My Rin is going to equal my R1 in parallel of R2. That equals 7 megs in parallel of 5 megs, which equals 7 mega ohm times 5 E6 divided by 7 E6 plus 5 E6. I got 2.92 mega ohms, which is a really large input resistance. Then we got R out, which is going to be equal to, and then R out is going to be approximately RD, which is going to be 1.2K. And then we're going to have AV we need to determine. That's the last thing. Well, AV, these are now dealing with your AC or R in, R out, and AV. It's going to be, remember, we have negative RD over 1 over GM plus RVES. Well, RVES here has a bypass capacitor, so this goes to 0. So it's just negative GM RD. Okay. And so we know our RD, but we don't know our GM. Remember, GM is equal to the change in ID over the change in VGS. And so what we need to do here is we need to see what our GM could possibly be. And so this one, it's a little bit harder sometimes to determine your G of M since it's like the tangent line. And so it can be harder with these curves because they're a little more exponential, so you can't get like the correct point for it. And what I would suggest, let me see, did he give us our K values? Okay, so if you had to do it, my best thing I would say is to, when you make your tangent line for the ID over, let's see, does that loop tangent? Let me change the color on that so it doesn't. We had to make a tangent line here. Say about there. So it looks like a change of about, you have to see how much change is there in voltage versus how much change in current. Well, here the current is 5 milliamps, right? In between here, 5 milliamps. Over the change in voltage, which is here, which is about 2.1 to 2.3. So that's about 0.2 all over, and then this is 5 milliamps, which is 5 milliamps divided by 0.2, we should get 25 milli Siemens. So negative 25 millisiemens times RD, which is 1.2K, which is 25 millisiemens times 1.2K. I got 30, which is a larger gain because we have a bypass capacitor. We're used to seeing gains in like tens or something for MOSFETs, but because we have a bypass capacitor, that's why we have a gain of 30. Oh, sorry, negative 30. I always forget that negative sign. Okay, now that we determine how to actually analyze one from the graph, this is pretty good. You will have to know how to design one in particular, and that one can be a little bit of a complicated process specifically. And so, okay, so here's a design problem we could probably be asked. So let's just try and learn how we should approach this. And so for the design for the MOSFET, it has this set we're used to seeing for MOSFET devices. Then we have here, and if they meant to draw the open terminals on this one too, suggest an enhancement mode MOSFET. He wasn't. So just draw the open terminals even though they're not there. And then we need to have this connected to ground, and then we have another resistor, negative 15 volts. So design for ID equals 3 milliamps. And so we have a supply negative 15 volts. And so if we were to choose our specifics, we want to use combination biasing, so we stay around 3 milliamps. And if I had to decide how much voltage do I want to put here, I don't want to use too much gate to source voltage at the same time because that takes less voltage from being on my RD, so that means less gain already. But let's choose about 5 megs and 10 megs. And so that means I have 5 volts here. So that's the good process. We can try and determine that. We have high input impedance. That's why we have 5 megs and 10 megs. And then we're going to determine our RFS here and our RD. And so what we need is basically, we need to determine what we have for this one here. And so we're going to go, let's see. This is 5 volts. So let's determine where the 5 volt point is. It's about there. I'm going to say it's about roughly here. It might be off in my estimate, but close enough. And so we determined our voltage. And then if we need a 3 milliamps, this is going to be, let me redo this so we can get the typical curve. Let me draw that in here. Our typical curve would be between these two. Okay. We need the typical curve to intersect with 3 milliamps because that's the typical. So if I'm looking, here, would this be about 3? At that point, because when we backtrace it here, this will hit roughly 3 milliamps. Oops. And so that's where we're roughly between. So the slope of this line is what we have to determine to get our RSS value, because this is 1 over R of S. Well, that's going to be the change in the voltage over the change in the current. So here, this is about like 1.8, I would say. So it's about 6.8 all over, and then it's going to be the current. The changing current here is 3 milliamp, or wait, no, sorry, from this point, what was that point specifically taken? It's about roughly 3.2 or something. That's what I would guess it as, over 3.2 milliamps. And that is going to equal 6.8, change in voltage over change in current, 6.8 divided by 3.2 milliamps. I got 2.125. kiloohms, 2.25 kiloohms. So I got 2.125 kiloohms, and that's to operate. So we get an ID of 3 milliamps. Now we need to determine our RD. Well, our voltage on RD is going to be equal to VDD minus. And then here's the point where our equation comes into being. So we need to do here, our supply is negative 15, or we can just start with 15 because we'll make everything else negative, and then minus. Our VP max, when we're looking at that curve in particular, that's given by the fat channel here, which is 5 volts. Then our VG, the voltage at the gate, that's going to be, we determined it was 5 volts. So we're going to have voltage at the gate. This was in the positive realm. So what we're going to see, these will add up together. So this was -5 minus 5 is -10. So let me come +10. Okay, -15. Oh, okay, I know why. This is actually -15 volt supply. So this is -5. So it's actually minus negative. So then becomes, oh, okay. So wait, this is -15. And then it would be, all these are going to take away from that value. And so this would be, and then here we have, voltage at the gate is -5. So that becomes 10. This is actually plus, then plus the voltage offset, which is 2 volts per offset. We have to do just the inverse of the signs because we're working with a negative supply. And so -15 plus 10 plus 2, that leaves me with 10 plus 2, which is 12. So -15 plus 12, that reserves 3 volts. So VRD equals 3 volt, -3 volts. We're gonna have -3 volts divided by the current that's running through it. So RD, well, of course, the resistance has to be positive, so that'd be 3 volts over, and then the current running through it is 3 milliamps. And that's going to be 3 volts divided by 3 milliamps. That should be 1K. Let's see, 3 divided by 3 milliamps, 1K. So I got 1K ohm. And so what we're going to see is our AV is going to equal, and then this design does not have a bypass capacitor in it. So it would be R of RD all over 1/GM plus R of S, which is going to be, oh, negative, sorry, I always forget that, -1K all over, and then we're going to say that it's approximately just RS for that denominator, which is 2.125K ohm. And you're going to see that we chose a VG. We need to go back and redo our design because our AV was -1000 divided by 2.125K. We got a smaller gain than one, -0.47. So knowing that, we would either have to adjust our VG value, and so our stability and our current won't be as good, but we could then put more voltage on this resistor. And so then if we could put more voltage on this resistor, we get a higher resistance value, so we could get more gain. And so that would cause us to go back. So the main things you'd have to, if you see that your gain is less than 1 here, it's not really providing enough, you have to adjust your VG. The thing is, if you adjust your VG, it's just going to be, if you make it smaller, it's going to be more variance in where that min and max point could be, but you could get your typical. So then this would be smaller, so therefore this would be smaller, so you'd have more voltage on your RD, and so then your RD would have a bigger resistance value, so then it could be a gain higher than 1. So this would affect your RD value here, and so your gain would be higher than 1. So that's how you go back and fix the design issue. And then now we'll talk a little bit about op amps, get into the last one. So how do we approach op amps? And so there are various types of op amps specifically in the course. And so what we're going to see is the ones you're going to run into. Here we're going to notice the basic one. So let me pull that up on my notes over here and write down. So an operational amplifier, just to start off, it has high input impedance. And so here at both terminals, I like to call this the VP and then the VN, one at the positive terminal, one at the negative terminal. And it has a supply voltage VCC. This is plus VCC and minus VCC. And it has an output voltage. And the constraint of the output voltage is that it's limited. It can never exceed the supply minus 1, and then it can never fall below negative VCC and then plus 1. It's always within 1 volt of the supply voltage. And so that means like if the supply was 15 volts, the output can only go from negative 14 to positive 14. And so that is the main thing. And then it has infinite input impedance at its input terminal. So there's no current basically coming through. And then the output impedance is very small. So for an op-amp, it has 2 different types of configurations. What you're going to see down here is open loop and closed loop. Closed loop corresponds, basically there's a feedback to that negative or inverting terminal, where open loop, there is no feedback here to the negative terminal you see in either of these designs. So that's the main difference between open loop and closed loop. So let's start with open loop with our voltage comparator. And so this is going to be one voltage source, V in, and this one is going to be, I'm going to call this actually, well, it's fine. I'll tell you what I'm going to do to make this easier. And then we have our negative and our positive, and then we have our V out, which equals the gain. And then here I'm going to call this VP, it's the voltage at the positive terminal, and here I'm going to call it VN, the voltage at the negative terminal. It's VP minus VN multiplied by the gain. And so we got this. So this is the voltage comparator. And basically what it does is it's going to compare between these 2 voltage values. And because the gain is infinite in an open loop configuration, it's going to either, depending if this is a positive or a negative value when you subtract the difference, if one waveform is larger than the other, then it would multiply that by your gain to give you infinite. So say this was like cosine of, I don't know, like t or something, and this is sine of t. Well, you're going to plot both of them on the input. And so we have our, I'm just going to do the sine sinusoidal one, something like this. And you have your cosine. Something like that. Okay. And so you would notice at these points right here, like where it's changing between one is greater than the other, something like that. But maybe this should have been more at the origin, sorry. But what you need to notice is that at some points, one waveform becomes larger than the other. See, the green one's larger than the pink one right here, and then the pink one overtakes it, then the green one overtakes it, and then the pink one. So this, if our V of n is the sine, so this is our V of n, the pink one here, and this is our VP. So right here in the beginning, VP is larger than Vn, so this is a positive number. A positive number times infinity. Remember, our output voltage is limited within 1 volt of the supply, so it's only gonna, if our supply here is 15 volts, just a positive negative supply, this is limited to 14 positively and negative 14. And so here it's going to go up to 14 volts in the beginning. And then at this point where it changes, where the pink one becomes larger, that means that your V of N is actually greater than your VP, so it becomes a negative number. And so a negative number multiplied by infinity, well, remember, your output voltage is limited by the supply. And then at this point, this one, the positive becomes larger. Then at this point, negative becomes larger. And at this point, positive becomes larger. Looks something like that. And then, so it's basically just, it's comparing the two values, which we saw here. Is VP or V of N larger? If VP is larger, then it's going to be in the positive region and limited by the output, by your supply within 1 volt of it. If it's negative is larger, then it's going to be negative times infinity and it's limited within 1 volt of your supply. So it's negative 14. Okay. Now we talked about that. Let's get to, this is just a voltage comparator for regenerative feedback. Okay, I'm gonna give us a 4-minute break just so I'll be back though. Okay, so here's our voltage comparative with regenerative feedback. It just gets rid of the noise, so that's why we like it. Here's our feedback resistor, RF. And then here's our output. Our output is equal to the gain, and it's VP minus V of N. And so what we're gonna see here though is I'm labeling the Vn at the negative terminal, VP at the positive terminal. VP is given by voltage division. Is look at here. If you make a voltage division equation for VP, you're going to get VP is equal to V out multiplied by RS all over RS plus RF. So that's what we get specifically there. And then that's what we plug in, and that's how we found our regenerative feedback. The equation, how we use it, it's just a voltage division signal. Our closed loop now has all the connections between the output and the inverting terminal. Output and inverting, output and inverting. That's why it's a closed loop. So here we're going to just run through all of them. And so the inverting amplifier, if we do that, for inverting amp, it is going to be, it has R of S here, then we have R of F, and then we have our inverting, and then this is hooked to ground, this one, and then R of S, voltage input, and then we have our output voltage. And our output voltage is going to be given by, and so here, it's at the inverting terminal, and we have negative RF or feedback over the other resistance times the input Vn. And then your one that I like to say just, I guess the analog inverter he likes to use, but the only difference in the analog inverter, I'm just gonna write down the main ones that you should be familiar with. The analog inverter is the exact same thing, but just look, the RS is value is actually RF, so it's exactly the same as RF. So it's just RF over RF, so that's why it's just like a 1. So that's where the analog inverter comes in. The inverting summer, you'll see this one. So in other courses, so I'll write this one down. Inverting summer. It's just basically a summation of inverting amps all put together. And so here if you have a VA and you have a RA, then you have a VB and you have an RB. And then here you have a VC and you have a RC. You're going to have all these connected. And so then you have an RF. And then you have, it's hooked up all to the inverting terminal, then your positive. And then this is your output voltage. Your output voltage is going to equal. Well, here we have negative RF over RA Vn minus RF over RB, VB, sorry, this is VA. And then minus RF over RC VC. Okay, so how do each of these come into existence? Well, let's just look at them individually. Cross out these two. You're going to see it's just an inverting amplifier. It's just the output resistor RF over RA in the voltage source. So just look at this one contribution. That's how you get this one. Then your next one, it is the next contribution, which is going to be this one right here, which is gives you the second one, and then your third one, which is going to be this one right here, which is given by this one. So it's just a combination of 3 inverting amps all in one. That's where the inverting summary comes from. And then your next one is going to be the non-inverting amp. That one you'll see fair amount. The non-inverting amp, it basically just has it now hooked at the positive instead of the negative terminal. So this is your R of S, and then you still have your R of F. Then here you have your voltage source, V in, and then you have your output voltage, V out, but this is hooked to the feedback. So the voltage source is now hooked to the positive terminal. That's why it's non-inverting. And so you're going to notice your output is still going to be your input voltage, which is V in, then 1 plus RF over RS, and then this is 1 plus, and then your output over your input resistor. And the only difference here is because it's a non-inverting amp, that's why you do this way. And then your voltage follower, this one, it's basically, if you look here, let's compare it against the non-inverting amp. So this one is like 0 ohms, okay? So your RF is like 0 ohms. And then here it's like an open circuit, right? Because it's just like an open circuit, so you don't see the other side of it. You can sort of think of it like it's infinite resistance, so all the current would go through this way. It wouldn't want to go through the open circuit because that's infinite resistance. And so then you can think of this right here as infinity, right here. This one right here is infinity, so 0 over infinity is 0. So it's 1 times V in, so that's why we got voltage outputs equal to the input voltage. Okay, so now we need to look at specifically the errors, because Ari's big about these errors, and I'm sure something's going to come up about them. And then we need to get into the 3-op instrumentation amplifier. And so the types of DC errors, okay, that's the big thing about op amps. I forgot to mention that in the beginning, but they do DC amplification, so they're not affected by a frequency or anything. Like there's no specific, because they're only DC, they're not affected. So that's the nice part, is what we think about them. We don't have to worry about those AC errors with gain, the input, the output. No, we don't have to worry about those with op amps. And so the first one is offset voltage. And the best way you can say this is literally, instead of having your voltage source, just insert an offset voltage source. Because if he says like, if your offset voltage is like 5 millivolts, instead of your source, just insert the voltage offset. And so then instead of writing V in, just do V offset. And then here it's negative plus, then your output voltage. So remember our op amp, it's going to do, this is a non-inverting one since I have it hooked to the positive terminal, the source. So it's going to be your voltage offset, and then it's going to be 1 plus, and then your RF over RS. And that's how you get this equation here. Your next one is going to be the bias currents. So your bias currents, my biggest suggestion for this one is literally just know how the formula works and what it's trying to tell you. So this is your gain, right? This is your positive voltage, VP, your voltage at the positive terminal, and then minus VN. So it's literally just the gain and then multiplied by VP minus VN. That's what he's trying to tell you here for the bias currents. And so here, it's your R of S, and you have your R of F, then you have your negative, and then you have your positive. Your output voltage is equal to the source voltage, and then remember 1 plus RF over RS. That's your regular one, but for bias currents, it's going to be V out. Remember, this is just your gain right here. And this is your VP minus VN. And we notice that VN is 0 because there's only voltage source hooked to the positive terminal. So here instead, for your VP, it's going to be how much current IP. So this would be with no source. It's just looking at bias currents. And so IP times RG gives you your VP. So IP times RG would give you how much voltage is here. Then your I of N is going to be minus I of N, and then it's going to be R of F in parallel of R of S. And then this would be 1 plus, it's a non-inverting amp, so RF over RS. There you go. That's what you would do. And then your next one is going to be on correcting DC errors. And so this one just takes all of them into account. It takes bias currents, it takes offset voltage, and then it just shows you what all the contributions are and how to get rid of the bias currents and your offset voltage. So to finally correct the DC errors, it's going to add in like sort of this potentiometer here, which is going to help eliminate the bias currents and offset voltage errors. And so that's the reason why they put an adjustable pot here. And so negative, positive. RG here is your source resistance, and then you have VG. This is a variable tanker. Here's your output voltage, V out. And so your V out is going to equal then your normal op amp, right? If I look at this, it's an inverting op amp, so it'll be the voltage, then 1 plus RF over RS, and then plus. Well, if I had an offset voltage, instead of VG, I would just put V offset. So I'll do V offset 1 plus RF over RS. And then if I'm looking at the contribution by bias currents, I short the source and I just look at the voltage on the positive terminal. And this is the IP bias current, the IVN running for each terminal. And so the VP is IP RG minus the VN, which is going to be I of N. I of N, and then RF in parallel of RS. And then it'd be the gain, and it's still non-inverting amp, so 1 plus RF over RS. And so that would be all the contributions. This one is due to your normal non-inverting amp, so non-inverting amp. This one is due to your offset voltage. And this one's due to your bias currents. And then we have here is for our last section. It's going to be talking about, let's look. I thought he had it in here. Yes, these two. The last one you'll never see. And so this one is the differential amplifier. Which is going to be, you have basically, it's going to amplify difference, right? And so you have your V of A, and you have your RA here, your RB here. And then you have it hooked to your negative terminal. Output, and then here. RD is equal to RB. We got RC equal to RA. And then we have our VB here. Okay, so what is this going to do? So we're going to notice it's going to amplify a difference, and these resistors across from one another are set equal. So this one's set equal to this one, and this one's set equal to this one. And so that's exactly the same like in your 3-off instrumentation amplifier down here, where these are set equal to each other, the ones across from one another. So if you look right here, these are equal, and these are equal. So since they're equal, then that's the part that contributes to this part, and then it amplifies the difference. So that's why the differential amplifier. Then in the beginning, the only difference with the 3-off instrumentation amplifier is this is a non-inverting amp. So that's where this gain equation is coming from, because it's non-inverting. Okay, so this one is going to be, our output's going to be RF, or sorry, RB, I guess, in this example, over RA, multiplied by the input, and then minus the other one, because it's a differential amplifier, amplifies the difference between, oh, sorry, it's the positive minus the negative terminal, like always, VP minus VN, VB minus VA, and then now we got that. And then our 3-off instrumentation amplifier, what we need to do for that one, 3-off amp instrumentation amplifier. This one's a pretty large one. It's one to know about because it pops up a lot. And basically what you need to do is you have 3 op amps. You have 1, 2, 3. You have your negatives in the middle, and then copy the last one. That's what I think. And then here, you're going to have your 2 resistors here. And you're going to have a feedback resistor for both of these op amps. See. Oops, need to connect it over here. And then you're going to have it hooked back. So here's your RVS, here's your RVS, RVS, and then here's your RVF, RVF. And then you're going to have your R of A, and here's your RB, then hooked to your output. And so this is your RB, here's your R of A. I'm going to label this resistor exactly the same as R of A, since the ones across from each other are equal. Then this one's hooked to ground, so R of A, R of B. And then this is hooked between the positive and negative terminal. And then here at the inputs, you're going to have your VA, your VB. Okay, and then the output here is going to equal, and then it's going to be the gain of the non-inverting amp at the first stage, which is 1 plus RF over RS. Then the gain of this one here, which we talked about earlier, which is RB over RA, multiplied by the difference in voltage. And so here at the positive terminal, we'll have the VB minus VA. Okay. And that's the 3-off instrumentation amplifier. And basically you just apply these to all the questions that you might be given. And it should be pretty good. We'll do one design problem. And so let's look at the one. I think it will talk, I want to do the design with the 3-off instrumentation amplifier. And so let's go to that one real quick. This one here, design a 3-off instrumentation amplifier with a gain of 100. And so this one right here, 3-off instrumentation amplifier, and we want a gain of 100. So what we would do is if we want that, right here I have my diagram for the 3-off instrumentation amplifier. And this part right here is all the gain, right? And so if we want our gain to be 100, what if I made this 99 for this part right here? And then what if I made this 1? So it'd be 1 plus 99, which is 100 times 1. So then this RF here, it would be 99K, 99K. And then what if I made this 1K? 1K. Then here I have 1, so then I could choose like 10Ks for these. This 10K over 10K would be 1. This one would be 10K, 10K, because they have to be the same across from one another. So then that would give me a gain of 100. And so that's how you would achieve that one. If we wanted to do one other one, let's look at this one here for 3A. And so if I'm looking at this, I'm like, okay, this is an inverting amplifier since it's hooked to the negative terminal, the op amp, the source. And then I would say, okay, now if you're knowing inverting, it looks like we have our R of F here. And then we have our R of S right here, which is 10K in series with 2K. So that'd be 12K. The series combination, those two. So your output voltage would equal your input, which is 100 millivolts. And then multiplied by the negative of your RF, which is 20K over your R of S, which is 12K. And then that's how you would get your output. So I get 100 millivolts times negative 1 because it's in times negative 20K divided by 12K. I got for my answer, I have negative 166 millivolts when I do that. So I get negative 166 millivolts. And that's how you would do a simple op amp configuration. You'll notice a lot of times they have DC sources since op amps are DC amplifiers within their devices. So you know. And that should sum pretty much up the MOSFETs, JFETs, and operational amplifiers.